talking about last day was resonance. So when we talk about resonance, we're talking about something that's a result of standing waves. And specifically standing waves in a body when the applied frequency that a medium, now the body is the medium, is vibrated at matches what we've called so far the natural frequency. Okay, so the natural frequency of that body. Now, what resonates or can have a standing wave really depends on what the body is. So in an object, that's the question. I want to focus on an orchestra. So in a musical orchestra, we think about air resonating. And specifically, we might talk about one of the woodwinds or a brass instrument. So we would talk about air resonating inside of something like a flute. We might also talk about, in an orchestra, the solid structures resonating. And when I say a solid structure, a good example of a solid structure that resonates is one of the bars on a xylophone. It's a solid, not a gas. And then another thing that might resonate is the strings. And for example, we could say like on a violin strings resonate to make those noises. They have standing waves that are formed on the strings themselves. Now, actually, here I am talking about a violin. A violin actually has all three of them. Because if you've never noticed this before, you know the violin, guitars have it too. There's that air opening right over top of the strings. And that air opening is designed to allow vibrations from the strings to enter into the air cavity within the instrument. And that causes the air inside the instrument to vibrate, to resonate inside of the instrument. The other thing is the wood that the instrument is made out of. We all think of like a Stradivarius violin or something like that. A Strat has a specific wood structure to it. That design allows the wood to vibrate. And that vibrating wood is an example of the solid that's vibrating. And so here I am saying, oh, we have flutes have air resonating and xylophones have solids resonating. Really, like the truth is, a lot of these instruments have multiple things resonating simultaneously, okay? And string instruments are a good example. A grand piano, you can imagine the housing for that piano vibrates as well, right? So if the resulting vibration has a high amplitude, I don't know why I just capitalized the word amplitude, but if it has a high amplitude, it can, here I will capitalize this, destroy the body that's vibrating. And I'll put up some videos and things in a few minutes, but one example of something that experiences resonance, and actually does reach the breaking point might be, and here I have a picture of it right here, a wine glass. If you play the frequency that's the natural frequency for that wine glass at the wine glass, you can actually get that wine glass to vibrate, and as it vibrates more and more and increases its amplitude, hey, look, this is a low amplitude wave. This is a high amplitude wave that has the same wavelength. Can you imagine if this was a string and this string and this string are the same length? Can you see how the second string with a higher amplitude has to be stretched more? If it started off the same length of string, higher amplitude means you're distressing that material more. And of course, that's what's happening with this wine glass. If you play that fundamental frequency, that natural frequency, louder, eventually it'll get to the point where the structure gets stressed and it shatters. Okay, so building up that fundamental frequency on a wine glass causes destruction. Another example would be a mass on a spring at resonance. And people even give a name for this. It's a spring pendulum. Now, not every pendulum goes back and forth. There's a torsion pendulum, which twists back and forth. There's a standard pendulum, which swings back and forth. And there's a spring pendulum that bounces up and down. So this would be an example of a spring pendulum bouncing up and down. C, a singing rod. And when I say a singing rod, yesterday I dropped a metal rod on the floor, hoping that the chemistry teacher would hear it from above. So they're below us. Not that chemistry is beneath us. Somebody told the chemistry teacher that I said that, but I didn't mean it. Didn't mean it that way. Physically, he's beneath us, though. And when we drop a rod, I was hoping that he would hear it, but I guess not. Anyway, that singing rod is the rod that's vibrating with its natural frequency, its fundamental frequency. And a tuning fork, or exciting a guitar string. Now, something that maybe you don't know is if I play a guitar string at exactly, here's a tuning fork. This tuning fork has the number 2048 written on it. That means that it resonates at 2048 hertz. If I were to play a guitar string at exactly that frequency next to this tuning fork, the vibrating air would cause this tuning fork to actually start ringing, because that's its fundamental frequency. That's its natural resonance frequency. So the tines of this tuning fork, and if you didn't know the names of the spikes on a fork, every fork, whether it's a tuning fork or one that you eat with, the arms, the spikes, are called tines. So the tines on this tuning fork would resonate at 2048 hertz. And if I play a 2048 hertz sound source near this, it'll start to vibrate sympathetically, just because the air particles bump into it at that rate. Yes?
You had a tuning for like different proportions, like a bigger one or one that's a bit wider at the base.
Yeah.
Still vibrate at the same hertz, or
Well, I'm glad you mentioned that. If I had a different tuning fork that's a different dimension, you notice that this one here, different dimensions, is 512 hertz. It has the number 512 written on it. So the longer the arms,
the higher the frequency.
well, the lower the frequency. Turns out that longer wavelengths can fit into this tine. So longer wavelength means lower frequency, right? So a shorter wavelength is going to mean a higher frequency. So if you got tiny little tuning forks, high frequency. Great big tuning forks, low frequency. And the numbers stamped on them kind of tell the numerical story. This is 512, this is 2048. Now, we could also talk about how thick the tines are and all that sort of thing. So obviously this is something that you'd have to determine experimentally with the particular metal that you're talking about, the thickness of tines, the length of tines. But in the end, you'd want to have these guys stamped on so you don't forget it. You also might notice that 512 is exactly 1/4 of 2048, right? There must be something to that, because it turns out that this is a C note, but this is also a C note. One's a higher C than the other. And if you play piano or any instrument, you might notice on your instrument that they are higher and higher octaves, right? Tell me you know what I'm talking about. So the C note repeats multiple times across some instruments. And so notice that the C note would be integer multiples of each other as we go off those octaves. So we'll come back to that idea of integer multiples later on as it relates to music. Another example would be in 1940. There was this bridge at the Tacoma Narrows. This bridge is in California, and I got to drive over it one time on a family holiday. Not actually, that's not true. I didn't drive over this bridge because this bridge broke in 1940. I drove over the Tacoma Narrows over the new bridge. The new bridge is perfectly sound. It's a well-structured bridge. It has not fallen apart as yet. But the idea was that this original bridge back in 1940, they started it in 1938, the bridge was destroyed by wind. And an example of something where you've probably caused something to resonate by blowing wind across it. You guys ever picked up a blade of grass and you hold a blade of grass between your thumbs and you make like duck calls? You know what I mean? Like that kind of sound. What you're doing is you're blowing between that gap in your thumbs and you're holding a piece of grass in that location. And as you blow, you're adding energy to the grass and it's going to vibrate. What happened was there was this bridge and it was in a narrow, so basically like a valley, a channel of water where the wind blows strongly. And just like the blade of grass between your thumbs, the wind blew across this bridge and the wind started to resonate just like that blade of grass. And if you've ever blown on a blade of grass hard enough, eventually the blade of grass breaks, it snaps. You've added enough energy. This is what happened to the bridge. Even though this bridge was 8 feet thick steel. Wrap that around your head for a minute. You might be 5 feet tall or 6 feet tall. This thing was 8 feet thick. That's a thick bridge to be like an analogy for our blade of grass. That's a pretty thick blade of grass. And yet the wind did it. It got it to resonate. And in its second harmonic, we'll talk about harmonics in just a minute. In its second harmonic, it stressed out the structure of that bridge so much that it snapped, just like that string that I was talking about earlier. Okay, and so I'll bring up some animations and talk about this in animation soon. It's been brought to my attention that if I bring in the animations, it knocks out my audio, so I won't do that during the video. I'll show the class afterwards. If you're watching online, you can watch all these videos and simulations and stuff on the online platform. All the links are available for all the videos that we're going to show in class. Okay. All right. So I want to take a look at what we mean by having harmonics. There's this mention here of first, second, third, and fourth harmonics. And I want to start out by putting a little dot here. And I want to count over 1, 2, 3, 4, 5, 6, 7, 8. And I'll put another little dot here. And I want to talk about the first harmonic. So first harmonic. And if I was going to talk about the first harmonic, it would look like this. I'll show you in the animations in a few minutes, but you can imagine that this is a picture of an animation where a string vibrates up and then it vibrates down. This is a standing wave. And if this string had a length of, I'll just call the length capital L, we'd have a string of length L experiencing its first harmonic. Now, it's language, so there's always got to be synonyms, And music is such a thing that people around the world play music, and different people talking about it call it different ways. But in English, at least, another way to say first harmonic is to call it the natural frequency. And I've already used that word once today. Unfortunately, there's a second synonym. And I've used it today too, kind of just casually. It's called the fundamental frequency. And so far we say we've got three synonyms. The first harmonic, the natural frequency, and the fundamental frequency are all the same thing. Okay? So if you see that in a sentence or somebody's talking about it, they all mean the same thing. Now to add on to that, here we are physics people, not just music people. And as physics people, we got to come up with a variable for it. So the first harmonic gets written as F1, F subscript 1. That's the first harmonic frequency. But here's the annoying thing. And this is something I don't love, is that some people will call the first harmonic or the fundamental frequency or the natural frequency, some people will call it by the variable F subscript 0. F naught. British people will call 0 naught, right? So F naught is the lowest frequency. The reason I don't like this is because F1 makes me think numerically of the first harmonic, whereas F naught doesn't make me think that way. I'm going to use F1. If I accidentally use F naught, forgive me. If you see F naught online or in your textbook, you just need to know what it means, okay? So we know that, unfortunately, we have 1, 2, 3, 4, 5 different ways to say the same thing. 3 of them are in words, 2 of them are algebraic symbols. All right, so I want to give myself a little break here. Maybe I'll grab myself a ruler, draw myself a vertical line just to break up my page a little bit. And I want to look at the second harmonic. Now, the nice thing is there's not so many synonyms for the second harmonic. First harmonic shows up a lot more frequently when we're playing music and just talking about like a pure tone note. Probably that's the reason, okay? So second harmonic, though, I'll count off my squares again. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Second harmonic, we talked previously about nodes and antinodes. I'm going to put a little dash there because there's going to be a node at that spot for the second harmonic. Second harmonic looks like this. Here's one extreme position for the string. Here's the other extreme position for the string. And so again, the solid line and dotted line represent 2 snapshots in time for an animation. And again, I could show you animations of different harmonic waves for standing waves. But one thing that we could say is that if this string is the same length as the previous string, call it L. If this wavelength, the second wavelength, is half the wavelength of the first one, remember, I'll just make a note off to the side. I know that V is equal to lambda F. So if the speed of the wave that's bouncing back and forth in this string is constant for the first string as compared to the second string, if the wavelength decreased, what does the frequency do? Yeah, frequency increases, right? In fact, it makes sense that if the wavelength just went from being this long to being this long, see how the wavelength just, that's actually half a wavelength. Sorry, if half of a wavelength went from being this long to this long, you guys see that the wavelength just got cut in half? So if the wavelength gets halved, you imagine that the frequency gets doubled? That's a proportionality thing. That makes sense. So what I would say is F subscript 2 is equal to 2 times F1. So twice the original frequency is the second frequency. Or what people would say in a sentence is the second harmonic is double the first harmonic frequency. Now, unfortunately, because I could have said F1 or F naught, some people will write it as F2 is equal to 2F naught. I personally prefer the first version for the reason that I said earlier about, F1 reminding me of harmonic numbers, right? And F2 would be the second harmonic, obviously, right? So here I want to break up my page again, give myself another vertical line, and I want to do the third harmonic because the subheading says that we're going to do first, second, third, and fourth. So the third harmonic, I'm going to cheat. I'm going to cheat just a little bit. I'm going to let my string be slightly longer. I'll pretend that I didn't, but I'm going to cheat because it makes the drawing easier, okay? So if I say I'm going to count, I know these ones were 8 units long. 1, 2, 3, 4, 5, 6, 7, 8. I'll make this one 9. Why would I choose 9? Divisible by 3. Now, if I was somebody who didn't want to have to do this, and if I had maybe I was a smarter person and I made my grid bigger, can you believe that it actually would have made more sense for me to make these guys be 12 units long? Because 12 is divisible by 1. 12 is divisible by 2. 12 is divisible by 3. And yikes, 12 is divisible by 4. 12 is a really nice number, honestly. And this is, I've ranted and raved about our base 6, base 12 time system. But the fact that we have a base 6, base 12 time system and harmonic numbers somehow split up nicely into 12s, oh my gosh. It's like, I don't know, we're so hung up on the decimal system, but base 12 could be a thing. Anyway, Babylon. All right, so if we break this guy up into equal threes, then I would have my 2 extreme positions for this harmonic. And we'll say that the string is that same length, L, even though I did cheat a little bit and I had my little rant about 12 being a nice divisible number. Anyway, if I did do this, I could say, what about the third harmonic? What do you suppose is probably true about the third harmonic as it relates to one of the previous ones? Yeah. Yeah, F3 is equal to 3 times F1. In other words, the third harmonic is thrice. Don't get to use the word thrice very often conversationally, but the third harmonic is thrice the fundamental. True, okay? Thrice means 3 times. Sweet. All right, I'm going to break up the layout one more time for the fourth harmonic. Fourth harmonic. Anybody want to guess how many half wavelengths fit into a fourth harmonic? 4, yeah, okay. So I'll count off 8 again. 1, 2, 3, 4, 5, 6, 7, 8. I'll break out my nodal points with dashes. I've got my peak and my trough and my peak and my trough at one snapshot in time. And then at another snapshot in time, I would have a peak and a trough, a peak and a trough. Right? And if this ends up being also a length L, you guys got this. What's the fourth harmonic's frequency? What? Yeah.
4 equals 2F2.
You could say 2F2, but I want to base it on the fundamental. Yeah. 4F1. Yeah, everybody says 4F1. That's how we roll. You're right, it is 2 times F2, but we use the fundamental frequency as sort of like a measuring stick. And so the general equation goes like this. F sub n, where n is the harmonic number, is equal to the harmonic number times F1. Of course, you could write it as F sub n equals NF naught, but that's not what I like. So that's just a style preference, honestly. So just a reminder that that n value is the harmonic number. Now, on the other hand, yes, not necessarily, but you can always have a ruler. So I may or may not give you grid paper on a test, but you should be able to have use a ruler. Okay? Yeah, draw a scale diagram. Yeah, you can absolutely do that. I might give you grid. Depends on how nice I am that day. Okay? All right, so another thing that I notice. Oh, yes, sir. Oh, it's just the way I drew it. The amplitude doesn't necessarily decrease. Yeah, don't read too deeply into that. Although it actually might. It might be that because there's elastic limits to our string, the amplitude might go a little bit quieter. That's true. But I wasn't trying to communicate that. I want to do this other thing. Look, can we notice that for the third harmonic, the length of this string is equal to 3 times lambda over 2? For this fourth harmonic, the length of the string is equal to 4 lambda over 2s. Now the L value, the length of the string, stays the same, right? So clearly the only thing that can give is the wavelength's getting, what, longer or shorter as we get to higher harmonics? Shorter, right? You can see that physically. It's getting smaller. So what we could say is, hey, this 3, 1, 2, 3, this 4, 1, 2, 3, 4, isn't that actually the harmonic number? So what I should do is this. I should say something like this. L is equal to n times lambda over 2, where again, n is the harmonic number. So if n is the harmonic number, same n, okay, then we have 2 formulas here. One that relates harmonic number to wavelength and the length of the resonating body, one that relates the harmonic number to the frequency for that harmonic relative to the original harmonic. Does that feel good to everybody? All right, so we're being mathy here. I had some people complaining that we didn't have enough math yet in this unit. There we go. More math, okay?